All right, so the topic today is inequality interval testing. It's going to start quite similar to the stuff that we learned yesterday about inequalities, but we're going to get into quadratic inequalities now where we actually have an x squared involved somewhere. So let's get going. First things first, we'll recap linear inequalities. This is the stuff we did yesterday. Then again, like I just said, we'll look at quadratic inequalities and interval testing with one variable. So in other words, we're not going to throw y into this. We're just going to stick with one variable, just x. But we're just going to deal with quadratics as well in this one, that's all. And then we'll throw some practice in, of course. Now, don't worry about that last little bit. So keep in mind, our unit exam is on Thursday. It's actually going to be on Wednesday, the 13th of January. This was an original plan that I had done before. We just took a little extra time that I thought we were supposed to have it actually Thursday the 7th, which is the day that this is supposed to even air. Ho ho. Anyway, don't worry about that. Let's get going. All right, so a review of yesterday. I would really appreciate if you just pause the video here and give this one a try, and I will go over it in just a second. All right, I'm going to go over this one now. First things first, we want to get our y all by itself. So let's move our 10x over. So I'll subtract 10x from both sides. That's going to give me negative 5y is greater than minus 10x plus 20. Then we want to get y totally by itself. So let's divide by negative 5. Just remember, though, when you divide both sides of an inequality by a negative number, you have to flip the sign around. So now it has to be y is less than. If we divide this by negative 5, we get positive 2x. And if we divide this by negative 5, we get minus 4. So 2x minus 4 is what we're basing this around. Notice it is just a strictly less than sign. It's not less than or equal to. That means when we draw this linear equation, if we were to have it as an equation here, when we draw this line right here, I should say, it needs to be a dashed or dotted line, not a solid line. So I'm going to start at my y-intercept here. That's going to be at negative 4. The slope, which is the number in front of the x, is 2. So we go over 2 up 2, or sorry, over 1 up 2, over 1 up 2, over 1 up 2, and just follow that through like so. And then just for good measure, we'll go the other way, over 1 down 2, over 1 down 2, over 1 down 2. That looks pretty good. And like I mentioned before, because it's strictly less than, we do a dotted line or a dashed line, whatever you prefer. So I'll just do a bunch of dots in here. Like I've complained about in the past using this pen tablet thing, it's actually almost easier just to do some dotted lines here. There we go. Still not perfect, but you more or less get the idea. Last but not least, we can't include anything on this line, hence why we did it dotted, but we have to include everything below it because it's y is less than 2x minus 4. So using the analogy from the other day, since it's less than, that means we're below this line. So if you thought of it as raining, we want to be under the roof. So that means we have to shade this side of that line because that would be underneath a roof. So it would be protected from rain coming straight down. Hopefully that analogy actually makes sense. It's made sense to me before, but I don't know, whatever. All right, so here's the new stuff for today. Quadratic inequalities, that's quadratic, right? So in other words, we got x squareds going on, but with one variable. Now, you might remember when we were doing inequalities with one variable, at least I believe we were doing them before. It's been a few days since I've recorded this. We have to only graph this in one dimension. A two-dimensional graph like we had on this last slide is reserved only when we have, well, two dimensions, x and y. When we only have one dimension, we have to do it on a linear line, right? So totally a number line, so in one dimension. However, that isn't exactly the most ideal when we have quadratics. And let me show you why. If we're asked what values of x make this true, we've got a little bit of a dilemma on our hands. You could start throwing things in here and seeing whether or not it's actually less than 24, but that would be pretty time consuming. What I would do in order to solve a question like this is I would solve for where this is equal to 0, not less than 0, but actually equal to 0. And then I would factor it just like we do any other quadratic to find where it's equal to 0. And then I'd set it back to being less than 0 as it would, or rather should be. That was a horrible explanation. I think it's way easier to see an actual example being solved. So when given a quadratic inequality, your primary goal is to factor it. This will give your x-intercepts, which we can also call critical points in this unit. Really, they're just your x-intercepts, so you don't need to worry about that term too much. These x-intercepts show where the inequality is going to change from being positive to negative and vice versa, as it, of course, would make sense. If you had a quadratic and you have your x-intercepts here, right before this x-intercept, you were positive. Right after that x-intercept, you were negative. Or again, vice versa. On this one over here, you'd be negative, and then you would turn positive. that's the whole point of an x-intercept. It just flips where you were, positive and negative, at least most of the time, other than the cases where you just kind of graze the surface of it. So it's your job to use interval testing to find out where the inequality is positive or negative. Now, interval testing means nothing to you at all right now. I will go back here because I was just wondering, we don't really have a huge amount of room here, but I'll do my best. Basically what this means is, like I said before, get one side to be 0. So I'll move the 24 over. We got x squared minus 2x minus 24 is less than 0. Now, if we imagine this being equal to 0, it just becomes a standard quadratic like we did earlier this year. We can factor this quadratic to help us find where this would actually equal 0. We're looking for two numbers that have a sum of -2, but a product of -24. Well, those two numbers would be -6 and +4. So we could write that as x minus 6 times x plus 4. And just for fun, we'll say that stays less than 0. Now, if this were equal to 0, we would be able to say that we have x equals 6 and x equals -4 as being our x-intercepts. In other words, the places where we are equal to 0. These are going to serve as some very important points that you could call critical points to help us check different intervals of numbers. Now, when I say an interval, like where did I have in here? Interval testing. When I say interval, that just basically means segments. If you put these numbers on a number line, so let's say we'll have -4 way over here and +6 way over here. Remember that your x-intercepts are where it switches from being positive to negative or negative to positive. It's up to us to figure out whether this interval is where we have an answer, this interval is where we have an answer, or if this interval is where we have an answer, or even some combination of those three parts. Your x-intercepts are the only locations where you could switch from being positive to negative or vice versa. That's why it's so important to use them as pivot points to check different intervals. Here's what I mean. Usually how I set this up is with a little table. At the left side of the table, I put my interval that would be the lowest numbers. So between 6 and -4, the lowest number there is -4. So we want to check the numbers, the x's, that are actually less than -4. Now bear with me on a second here. I'll just set up my other intervals. The next interval I'd have is between my two critical points. So between -4 and +6. So x is greater than -4, but less than 6. So it's in between those two. That's another interval we want to check. The final interval we want to check is where x is greater than our biggest x-intercept. So in other words, where x is greater than 6. Now what I do here is I just pick a number that satisfies this condition, and I plug it into this inequality right here, where I have it set less than 0. So you can pick any number you wish that satisfies the condition x is less than -4. And the purpose of this is we want to check to see if whatever we throw in there is in fact less than 0. So let's suppose we choose a test point of, how about x is -5. That just satisfies this. It's a little bit under -4. That'll work just fine. If you plug in -5 into this right here, you're actually going to end up getting +11. You can double check if you wish, but take my word for it. That is what we are going to get there. You will get +11 as your answer on that one. And +11 is, of course, a positive number. So because that's a positive number and we're looking for where this is less than 0, we can immediately go, that doesn't work, right? So we can cross that one out because it was positive. So that is not going to be one of our intervals that worked. So that one I'll just cross right out. Next interval we'll check is where x is between -4 and +6. Probably the easiest number to check in this case would be x equals 0. If you plug 0 into this, it'll be 0 minus 0 minus 24, which clearly will give you -24 as an answer. And -24, obviously, is a negative number. We are looking for numbers that are less than 0. In other words, we're looking for our negative numbers. So that tells me right now that this interval right here in the center is going to be one of our intervals that actually works. So that's good news, once again. Last but not least, we should definitely check this one here. X is greater than 6. Pick a number that satisfies that. How about we say x is equal to 7? Plug that into this guy once again. If you plug 7 into this, coincidentally enough, it's actually going to give us the same thing that this interval gave us. It's going to give us 11. And 11, of course, is a positive number. We wanted numbers that are less than 0, so this interval does not work. So our final answer here, how we would actually express the answer to this inequality, solving for where that inequality that we started with was true, you would say -4 is less than x, which is less than 6. That is your answer. All we're doing when we're solving this is we're just solving the range at which x is going to make that original statement true. Anyway, next thing you can do with this is check your answer, of course. Now, your graphing calculator can be pretty much your best friend when it comes to this. You can use your graphing calculator to confirm your answer. Just graph the one side of your inequality after you've brought everything to one side. So in other words, if you throw in your graphing calculator, x squared minus 2x minus 24, and then graph it, you're going to get a graph that looks like this blue graph right here. Now, quite clearly, we have an x-intercept at -4 and another one at +6. And what do you know? That range right in between those two is where we are less than 0. It's where our y is less than 0. So in other words, this whole area between -4 and +6 is actually going to be one of our solutions, or rather our entire solution set. That is the only area where our graph is going to be less than 0. Anyway, kind of neat. Moving on. Here's another example. It looks a lot beefier. And you know what? It actually is quite a bit beefier. Solve this inequality. We'll do this one together because, again, this is a really weird new concept. Hopefully you understand, though, the very first thing you should do when you solve an inequality is bring everything to one side. I think it would make more sense to move all this stuff over to the other side because 3x squared is smaller than a 5x squared. So if I take away 3x squared from both sides, I'm left with 2x squared. To move this minus 7x over, I have to add 7x. So that's going to give me a total of +6x. And then to move this +11 over, I have to subtract 11, which I believe is going to give me -8. And that's all greater than 0. Now, this right here is not just your standard sum product rule question. This is going to be one of your adapted sum product rule questions. Although, as I'm saying that, I just noticed there's actually something very neat I can do with this. You could use your adapted sum product rule to factor this. So in other words, you'd be looking for two numbers with a sum of 6, but a product of 2 times -8, which would be -16. And I'm sure you could do that. I'm sure there are two numbers that make that work. Probably could find it relatively quickly. But what I just was thinking of is I noticed that I could actually factor a 2 out of all 3 of our terms here. And that'll turn it into a normal sum product rule question. So if I pull a 2 out of all this, we've got 2 times x squared plus 3x minus 4. And that's all greater than 0. That frees up this thing right here, x squared plus 3x minus 4. That's just a normal sum product rule question. And personally, I find those a lot easier and a lot quicker to be able to solve. So we're looking for two numbers with a sum of 3, but a product of -4. Well, that would be +4 and -1. So we might as well say this is 2 times x plus 4 times x minus 1. And that's all greater than 0. Now, if we imagine, if only just for a brief second, that this was equal to 0, we would say that we have x equals -4 as one of our solutions, and x equals +1 as one of our solutions. But this is an inequality, so we actually have to check these points as intervals. So we use them as critical points in an interval test. Now, like I said before, I like setting this up as a table. So if I make a table just over here, just to do all my work, there we go. Always start with your smaller number because it's just generally easier just to think of your smaller numbers on the left and your bigger numbers on the right. So -4 is our smaller critical point here. So I'm going to say we're going to look at the x values that are less than -4. Then we're also going to look at the numbers that are between -4 and +1. So -4 is less than x, which is less than 1. And then lastly, we want to check the ones that are bigger than our biggest critical point. So we want to say x is greater than 1. So again, all you do is you just pick a number that satisfies each of these conditions. In this case, though, we're looking for where this answer is going to be greater than 0. So we're actually looking for something bigger than 0 in this. Okay, so a positive number is a successful solution in this one. If we're looking first at this interval of x is less than -4, how about let's plug in x is equal to -5. Okay. If you plug in x is -5, it's actually going to spit out from this equation right here, it's going to spit out +12, which of course is a positive number. So that means this interval is actually going to be one of our successful solutions here. Now let's check this middle one, a number that's between -4 and +1. Just like before, I think the easiest number to plug in there would be x is equal to 0. That way you can very clearly see it's just 0 plus 0 minus 8. So that'll spit out -8. And -8, of course, is a negative number. And for this question, because we're looking for numbers greater than 0, that's considered a failure. So in other words, we'll cross that interval totally out of there. Last interval to check is x is greater than 1. Probably a pretty obvious one to plug in would be x is equal to 2. Throw that into this equation or inequality. It's such a habit calling it an equation, but this inequality right here, plug it right in, and you're going to find once again that you're actually going to get +12 as an answer from that. And +12 is, of course, positive. That's a successful solution as well. So look at that. We actually have two intervals that are going to serve as positive, successful solutions here. So what you would use as your answer is x is less than -4 and x is greater than 1. And that whole thing right there would be your solution, because those are the intervals in which you will have a successful, correct answer that will make this statement right here totally true. Hopefully that makes some sense. We got one more example we're going to do here, and I'm just going to give you a bit of a heads up. It'll be a little bit tougher. Before I introduce it, let me remind you, on this one back here, we use just this plain old boring sum product rule. Okay, that allowed us to find our critical points. On this one right here, we could have used the adapted sum product rule, but then we kind of like cheaped out and we used the normal sum product rule, so it's whatever. What if you can't use those? Spoiler alert, here we go. So here's a tough example. Solve this inequality algebraically. No graphing calculators for these people. To the nearest hundredth. Uh-oh, it's always bad news when you see that, to the nearest hundredth. You always know you got something crazy coming here. Okay, first things first though, when you look at this, you might go, okay, well, we know, just like the other ones, we got to get one side to equal 0. So why don't we just move 10 over to the other side? We'll have x squared minus 4x minus 10 is greater than 0. At first glance, this one actually almost looks easier than the last one. But then you say, okay, well, this is just a normal sum product rule question. We're looking for two numbers with a sum of -4 and a product of -10. You can sit on that one as long as you wanted to, but you're going to find that your sum product rule is actually going to fail you here. There's not going to be two numbers that add up to be -4, but multiply together to give you -10, at least not off the top of our heads here. So we're kind of stuck on this one. If only there were some other algebraic way to find the x-intercepts of a quadratic, like some sort of formula for a quadratic. It's a shame that quadratics don't have a formula. Oh, wait, soik, they do have a formula. X is equal to -b plus or minus the square root of b squared minus 4ac all divided by 2a. That is on your formula sheet, of course. That's the famous quadratic formula. The quadratic formula is basically like the nuclear weapon of quadratics that you just pull out and you instantly win because it immediately solves whatever solutions you have to your quadratic. So let's bust this out. Let's throw in our values here. It's going to be x is equal to -b, so -4, so +4, plus or minus the square root of b squared, so -4 in brackets, really important, squared, minus 4 times a, which is 1 in this case, times c, which is -10, all divided by 2 times a, which is 2 times 1. Now, when you solve this equation, of course, you have to do it twice because of this plus minus. So if you did it with the addition, and usually I just denote this with x plus, if you did this with addition, so 4, that's a 4, 4 plus all this divided by 2 times 1, you're going to get 5.74. And that, again, is rounded to the nearest hundredth as one of your two x-intercepts. If you subtract it, so if you went 4 minus the square root and all that, you're actually going to find that you have -1.74. These are going to be your critical points. From this point, as much as it's really awkward using some decimal numbers here, from this point on, it just becomes the same as the other questions we had. Just turn it into a table and then check each of your intervals. To make a table, of course, pick your smallest x-intercept. The smallest one here is -1.74, so we're going to look for where x is less than -1.74. We're also going to look in between these two. So -1.74 is less than x, which is less than 5.74. Just because I never mentioned it before, this middle one often throws people just with how you have to write it. Always do your smaller one, then use a less than sign, x, then another less than sign, and then your big number. That way you'll always keep it straight. I don't know, just a little bit of a hint. Last one, we want to check the ones that are bigger than the biggest one. So x is greater than 5.74. Now, the good news is when you plug in numbers into this, you are not obligated to use decimal numbers here. Matter of fact, I think you'd be kind of crazy if you tried. If we just are looking for an x to plug in that's less than negative 1.74, why don't we just plug in x is equal to negative 2? That's a pretty safe number to be plugging in here. So if you plug in x is negative 2, and once again, that's into this guy right here, and we're checking to see that it's going to be greater than 0, you're going to find that you actually get, as a solution to that, positive 2. Which of course is a positive number. And because we're looking for numbers that are greater than 0, this is going to be one of our solutions. X is less than negative 1.74. Now let's check the in-between. Negative 1.74 is less than x, which is less than 5.74. Once again, it seems to be a really common one we get to do here. The easiest thing to plug in here would be x is equal to 0, because it certainly lies between these two numbers. If you plug 0 into this, you can see the solution right off the bat. The solution would be negative 10. Negative 10, no surprise, is a negative number. We don't like negative numbers here because we're looking for where it's greater than 0. If we were looking for where it was less than 0, we'd be in luck, but no, we're looking for where it's greater than 0. So we knock this one out of here. That is not going to be a solution. Last one to check here is x is greater than 5.74. We're probably all thinking of the exact same number to plug in. I mean, come on, it's just a number bigger than 5.74. We want something easy. Clearly, I'm thinking about x is equal to 5.944321. Just kidding, I'm thinking of x is equal to 6. Plug in x is equal to 6 in this one. If you do that, you're going to find once again that actually, coincidentally, x is going, or rather y is going to equal 2. Your solution is going to equal 2. 2 is a positive number. Positive numbers were what we were looking for here, so that is another solution. End of story here. What we're trying to get at is our two answers on this one that we have to list both of them once again to really confirm is x is less than negative 1.74 and x is greater than 5.74. There we go. Those would be your two solutions. You're all good to go from there. So we made it. For practice, I want you to try page 484, questions 1, 3 to 5, 9 to 13. But also your homework booklet, you can now do questions 1 to 5. You could do 1 to 4 yesterday. You can now do question 5 today as well. Because I don't want you just doing question 5 for practice, because this stuff is pretty technical, you really don't have much choice, guys. You got to be going back to these textbook questions. If you see one, like if you look at question 1, go, you know, Scott, that's baby food. I got that. It's no big deal. Move on. Pick through them. These ones are not assigned. So in other words, they're just used for your own general practice. If you see a question you already know how to do, don't bother doing it, right? Challenge yourself. Try some of the ones that you need to focus on. Anyway, as always, I'm available in the Zoom if you need me. Best of luck.